Okay, I wanted to talk a little bit about a question that I saw on homework number 6. It involves computing the surface area of an arc length that gets rotated around an axis. So this is the formula that we use for that. Since we're going to be rotating, finding the surface area, we need to find effectively the circumference of the rotation times the arc length associated with the arc that's being rotated. So the radius, when computing the circumference, ends up being perpendicular to the axis of rotation. So in this case, we're revolving around the x-axis. So I'm going to use f of x to represent that radius. And f prime of x is going to be used inside the arc length formula component of this. Now the function that we're working with is 30x minus x squared underneath the radical, so the square root of that quantity. And that's really a semicircle, but when we restrict our domain to x values between 1 and 6, we only get this portion of it. So if you can imagine that arc length being rotated around the x-axis, it's going to sweep out kind of like a bowl shape or maybe a plate or something like that. That's what we're discussing. So within the formula, we need an f prime. So I'll go ahead and do that. Let's remember that this is going to require the chain rule. It would be helpful to think of this equation as 30x minus x squared grouped under a 1/2 power. So if we use the chain rule here, we end up with 1/2 times the quantity of 30x minus x squared raised to the negative 1/2 power times the derivative of the interior 30 minus 2x. And if we take just a minute to clean this up, the quantity of 30x minus x squared can be rewritten as a radical in the denominator of a fraction. And then the numerator, half of 30 minus 2x, is just 15 minus x. While we're here, I'll note that the f prime will need to be squared as well. That's part of our definition, so we'll go ahead and do that. 15 minus x quantity gets squared, and in the denominator, when we have this radical that becomes squared, we'll just be left with the radicand underneath. And it will be helpful to notice that this 15 minus x, when squared, turns into 225 minus 30x plus x squared. Now, I always remind my students, although I know you all are never going to make this mistake, but please don't try to cancel the 30x's or the x squareds here. When we've got these terms separated by addition or subtraction signs, we can't just factor like that. So I'm going to leave that alone as it is and start plugging some values in, substituting some values in. So our boundaries of integration end up being 1 and 6. We want 2 pi times our function, which ended up being the square root of 30x minus x squared, times the square root of 1 plus the derivative squared. We ended up getting all the way down to here, so I'll just go ahead and make that substitution. 225 minus 30x plus x squared over 30x minus x squared. Okay. Now, I guess first things first, I could have avoided this entire expression here. If I wanted to, if I knew I was going to use the calculator, I technically could have just typed into the calculator ddx of radical 30x minus x squared. And I could have used this expression in place of the derivative and then wrapped it again in another parentheses to square. And this expression could have replaced this expression in my calculator, and I would have gotten a decimal answer, a decimal value off of the TI Inspire, and in some cases that would be just fine. In this particular case, though, MathXL does want an exact answer, so this is where some interesting algebra took place. Well, first off, what I want to note is that, well, we'll leave this alone. The 2 pi could be factored out. Let's go ahead and do that. So 2 pi is a constant factor. Pi is not a variable, so it's a factor. I'll pull that out front. But just remember, when I have a radical multiplied by another radical here, this act of multiplying, that's just like imagining, we've got a parenthesis group that's raised to the 1/2 power multiplied by another parenthesis group multiplied by the 1/2 power. There's a distribution that happens here with our exponent law. So effectively, this could become one just giant radical where I take this 30x minus x squared and multiply it by the radicand of the second radical, 1 plus 225 minus 30x plus x squared over 30x minus x squared. So I can multiply these two together. Now, why that becomes particularly helpful is hopefully you'll see this. If you imagine this term effectively distributing into this second term, you'll notice that we end up with, let's see here, our 2 pi integral 1 and 6. This 30x minus x squared times 1, well, that's just our 30x minus x squared. No surprises there. But when it multiplies into this fraction here, we could do the distribution and whatnot, but notice this quantity multiplied by the fraction whose denominator is the same thing will effectively get those two to factor out and cancel. And now we're left with 225 minus 30x plus x squared. And now take a look at this. All of these like terms conveniently will cancel each other as well. The 30x minus 30x, this negative x squared plus x squared, and we're now looking at 2 pi times the integral from 1 to 6 of the square root of 225 with respect to x. And now all of a sudden, what was a pretty wild-looking integral has simplified pretty significantly, and we're almost free now. 2 pi integral from 1 to 6 of 15 with respect to x. That's 2 pi times 15, so we'll call that 30 pi integrated from 1 to 6 of 1 dx. And using our fundamental theorem, we've got 30 pi times the antiderivative of 1 being evaluated at 1 and 6. So 30 times 6 is 180 pi minus 30 pi times 1 minus 30 pi ends up being 150 pi. And so that's a pretty nice and precise answer. And I was just doing some checking off the screen, and I ran this through the TI calculator. Let me show you exactly what I had typed. Sorry, it's on a different computer, so I can't show it on this particular screen. But I did ask the calculator to effectively compute this integral, and I did type d dx of the square root of 30x minus x squared, and I squared that expression. So this here, when I just press enter, not control enter to get intentionally a rounded value or an estimated value, but I just tapped enter to get an exact or precise answer, and it gave me the result 471.2389. So that's technically correct. It is equal to 150 times pi, except for whatever reason the calculator couldn't give me an exact answer this time. It left me with an approximate solution. So that 471 was not accepted by Math Excel, but the 150 pi would be. So I just thought that was kind of interesting in that, right now we're dancing that fine line. Are we using the calculator to solve our integrals, or should we be solving them by hand? Here's a nice case where knowing how to solve by hand actually gave us a better answer than even the calculator could provide. So I hope that helps, and if you have further questions, please reach out to me and we can chat more about them. Thanks.